Good morning for most of you, or good afternoon for the rest of you. Welcome to my talk about GCC. GCC is the new Pincc. Type on the first slide is intended, because for the last couple of months I've seen a lot of CC all over where I looked. This talk today is about GCC internals and what you can do for security when you work on GCC internals, or generally on compiler internals. And yeah, let's start over. Hello, this is me. My name is Marion. I'm a security researcher, and some of you might have heard I changed jobs a year ago, and back then I moved to Portland in Oregon to start work for Intel. And since I started work at Intel, my field of research has moved from, before I started work there, I was a malware reverse engineer, looking mostly into Windows, x86, 64, userland malware. And since I started work at Intel, my interest fields have shifted much, a little above and a little below x86. And for the last 6 months, I have focused on GCC. Before I start to show you more about GCC, though, like a little disclaimer. You might have noticed when you work for a large corporation, the office right next to you is full of very, very angry lawyers. And those lawyers require us to tell you that whatever we say, wherever we go, is not happening in the name of Intel or any of its affiliates. Also, we're not promoting and devaluing any product. All right, that was it, though. So, if at any point in your life you develop interest for compilers and you start to look into how modern day compilers work and what you can do with them, then you'll figure out you'll spend a lot of time looking at Hello World. This talk today I wanted to start with a little demo that shows what you can do with a compiler just only by looking at Hello World. So let's see whether this switch, yes. Oh wow, the switch to the VM worked. I'm very happy. Okay, so the first thing I wanted to show you today was literally Hello World. So when I take the microphone with me, oops, there we go. Okay, so we're in a folder where there is a hello-world.c file, which clearly does nothing more than printing a hello world. Have a close look at the string that's being printed. Oh, you can't actually see much here. That's very sad. Is there a way to turn off the lights? Can I make it dark? Please don't fall asleep. So if you would be able to read what's on the screen, here is a printf, and that prints a hello world with a \n in the end. So this is literally all this application does. And now if I go ahead and here is another command line that you can read. There's a GCC 7 that compiles the hello world.c to the hello world object that we can afterwards execute. So we compile this. Now we execute the hello world. And to that, printf's hello world. All right. Now, what I actually want to show you, I've prepared a little GCC plugin, which, if we look at the next command line that I've prepared here, is again the GCC 7. It compiles the hello world.c to the hello world executable. And the little change that I applied here is that it loads a plugin that says hello.so. So this is a GCC plugin which will plug into the GCC compiler passes, picks a pass where it can modify what the compiler outputs. Keep in mind I did not change the C file that I showed you before. So now I can compile the same C file with the same compiler with that plugin loaded, and then when I execute my hello world, all of a sudden it says Hail Satan. This is one of the funny things they can do when you look into a compiler. The plugin that does this is about 20 to 30 lines of C, and now let's have a look at how the plugin achieves this. All right, so our hello world just went Hail Satan. This happened because this routine that you see on the screen executed within the different passes that GCC executes to compile the binary, and this piece of code does nothing else but looking for a printf call. So it looks for a call statement, which is here indicated with simple underscore call, then picks out the first argument that this call statement contains, and at the bottom you can see it replaces the call statement with an API call to simple call set argument with a string that says Hail Satan. It sounds very simple. In practice, though, this is rather complex to implement. But the bigger part of my headache while I was working on GCC plugins was whenever I went up to people and told them, I work on GCC plugins now, it's super cool, and everyone's like, why? Like this, like, why? Why would you do that? Today in modern world, we have LLVM, we have Clang, we have things that are actually usable. They have nice APIs, they have documentation. Just think about that, they have documentation. And yeah, there's many good reasons why you would work on GCC that I could answer. It's like, most importantly, Linux kernel is mostly compiled in GCC. Then many firmware products, remember I work for Intel, many firmware products are compiled with GCC as well. Many important software products still compiled with GCC. But they all wouldn't count as much as some months ago. My team lead, which you all might know, his name is Rodrigo. He came up to me and asked me, "Do you want something challenging to do? Like I have an interesting problem here." And now I have a bowl of water too. I have an interesting problem here. We need you to write a GCC plugin. Do you want to do this? It's very painful. And I was like, yes, give me this challenge. And I didn't know what I was gonna start out on. I didn't expect that. So. When you start working on GCC internals, consider that there's a long and painful road ahead. And it turns out I like long and painful roads. All right, back to GCC. GCC actually stands for the GNU Compiler Collection. Of course, it has a website, it has documentation. There's a really thick book, about 700 pages, that tells you a lot about the GCC internals, as it's called, that lists all the APIs that you can use when you want to plug into the GCC compiler passes. GCC, like most compilers, I think has a front end, a middle end, and a back end, of course, and it can compile code. This is what all compilers do. This is what most people use them for. What most people don't know, though, is that you can also do lots of other things with the compiler. Like you could, for example, exchange the front end. You could come up with your own proprietary or your own fictional programming language and implement a new front end, and then use the rest of GCC, which, by the way, are about 14 million lines of code. So you could use the rest of those 14 million lines of code to compile your invented programming language to a given architecture. What you could also do is you could exchange the backend of GCC and implement a new CPU architecture. So you could write C code and compile that to your own CPU architecture if you're ever gotten to that position. Again, I work for Intel, so this isn't all that futuristic if you never actually thought about building your own CPU. Anyhow, you can also add optimization passes. The GCC middle end is mostly busy with optimizing code. You might be aware that coders sometimes write very inefficient loops, for example, and compilers don't like that. So they look at those loops and they make them more efficient and more performant, or maybe smaller. Furthermore, you can perform static analysis inside the compiler. You can insert flags, or you can add your own optimization passes that construct the output bytecode in a certain format, which might be easier for your analysis tools to understand, which is very helpful, for example, if you want to search for bugs. You can also look for optimization bugs inside of GCC, and something that caught my interest is that you can also introduce optimization bugs. I'll get back to that later. But yeah, you're very powerful when you work inside of the compiler. And now as we start looking at GCC more closely, I'll have to show you this picture because all the presentations that I saw about GCC started with this picture. It's called the 10,000-foot view onto GCC. And again, remember, GCC has 14 million lines of code, so like a 10,000-foot view onto GCC is very, very vague. But what you can see again on this picture is that there is the front end. The front end that's mostly responsible for parsing code. So if you hand GCC a C file or a Java file, then the front end is responsible for parsing that piece of source code into an abstract syntax tree, which is then translated to generic. Generic is the first intermediate language that's recognized by GCC. From there, from that language, the source, or like the intermediate representation of your source code, is then lowered to a representation called Chimple. Chimple is GCC specific, and it is, I think, inspired by an intermediate language called Simple that's used by a research compiler. which I don't remember now. Anyhow, so this representation then is used for the many different optimization passes that are architecture independent. So in the format of Chimple, the representation is still very close to the source representation. Chimple by itself actually looks very simple, very similar to C code itself. So that language is then used for target independent optimizations, and from there, finally, the representation is lowered to RTL. RTL stands for Register Transfer Language. I'll be speaking about all of those intermediate passes in great detail in a minute. RTL is very close already to the CPU bytecode, but RTL by itself in its initial state is still CPU independent. So it's architecture independent, meaning that from the initial state of RTL, we can still lower down to ARM, to x86, or to any given other exotic CPU that might be supported by the compiler. And RTL by itself implements the machine definitions which help the compiler lower the intermediate representation of RTL down to x86 bytecode or any given bytecode that we specified. That was GCC in 5 minutes. Now let's look at GCC in 30 minutes. GCC by itself is mainly split up into different compiler passes. This is a bit of an illusion. GCC likes to pretend that it performs its compilation in different passes, where one pass executes after another, which is exactly what happens, except that those passes aren't independent from each other, which one might think. So if we look at different compiler passes, those passes are responsible for parsing the source code, translating the source code, parsing intermediate representations, translating them, and lowering them to different representations. And this is all not done like step by step, but interleaving. One thing that I learned after looking for a long time at GCC is that there is an insane amount of macros in there and an insane amount of API functions. The API of GCC's internals is actually defined. There is documentation for most of those APIs and for most of those macros and for the constants that they're using. The thing is just that there are so many that writing a proper documentation with coding examples and wise hints on how to use the API would probably require more than a 700 pages book. The 700 pages book is what we have right now. Anyhow, the GCC compiler passes, though, are a nice thing to hold on to when you try to implement plugins. Because when you implement a GCC plugin, what you do is you add exactly one pass to the GCC passes structure. The GCC passes can be listed by the compiler itself. When you insert, when you execute GCC with the flag -fdump -passes, you get the whole list of GCC passes that are currently active. And then you can pick the pass that you want to relate to when you insert your plugin. More about this in a minute. But what I wanted to mention is that there's a really nice graphic that was created by one of the GCC folks himself. His name is David Malcolm. And my screen can't actually fit that graphic because there is about like 200 passes that are listed on the graphic. But if you're interested in which passes GCC executes, and more importantly, which data structures or which languages are available in which specific pass, then this graphic is what you should be looking at. What I mean with data structures. So you saw that GCC is parted in this front, middle, and back end, and there's different representations. And that means that the passes, they align with the different stages of the compilation process. That means that you have passes that relate to generic, then you have passes that relate to Chimple, then you have passes that relate to RTL, and then you have passes that relate to the lowering to the machine definitions. And that means when you want to implement a plugin, you have to be aware of what you want to achieve and where in the stage of compilation you can achieve your goal that you're out to get. So for example, when you want to implement a plugin that is looking at input parameters, like for example, you want to automatically verify input parameters in an application, then you might want to be closer to the C representation or to the source representation, because this is where the arguments, the function arguments, and input arguments are still clearly visible. On the other hand, if you want to perform modifications that are closer to the x86 layer or to the assembly code layer, then you're better off plugging into a later pass in the compilation stage, where you end up modifying the RTR representation or play with the machine definitions. This much about the passes. Another important thing to note, just so everyone's aware of that, GCC stands for the GNU Compiler Collection. I mentioned it already, but working at GCC also found out what that means. GCC actually isn't one executable that performs the whole compilation by itself, but GCC is really a collection of the CC1 or the CC1 Plus or the JC1 or the F951 or whichever front end you're using for compiling the source file that you're handing the compiler. So GCC by itself can pick the appropriate compiler to perform compilation of the source. And I might want to note that this CC1 stage, or like the first compiler stage, is what I'll be talking about today mostly. What comes afterwards is the GNU assembler and the linker. That's also called collect2 or LD. AS is what consumes the assembly text files that the compiler produces and lowers them to the actual bytecode representation. This was a bit of a surprise to me as well. When you look at what the first stage of the compiler, like the CC1 in the case of a C file, produces, you'll actually be surprised it produces ST text files. Those ST text files are the assembly representation that GCC generates from the source file. And from those text files, AS generates the bytecode. If you've ever looked at GCC, the -S option instructs GCC to not start the assembly stage. So with the -S option, GCC stops after the first executable, after the first compiler, so that you can inspect the assembly representation that the compiler produced. Anyhow, that just as a hint by itself. Another thing that is important to note before we talk about more internals, there's debug output. There's documentation too. Documentation is awesome, but documentation is 700 pages. The debug output by itself is super confusing. It's a lot. Like if you run all the debug output options, you end up with I think 40 to 50 log files each, and those aren't always easy to read. But if you know exactly which path you want to look at, or if you know which representation you want to study, then it is mostly easier to look at the log output than the documentation. At least that's what it was for me, in order to learn how a specific representation looks like and what you have to learn in order to be able to modify it. And what's more, if you're implementing plugins, with the -f dump option, you can dump specifically that one path that you're implementing in your plugin, so that you can look what exactly is GCC doing when you're executing your plugin and how to fix that. That's very important for debugging. Okay, but why do I keep talking about this GCC plugins? A good reason to look into GCC plugins becomes obvious when you look into GCC modification itself. So when you want to perform a change on GCC itself, first of all, you have to dig into those 14 million lines of code. And I haven't actually counted them, the numbers from Wikipedia, but I have a feeling it's about right. So like if you look at the code base of the GCC compiler, it's insane. So when you stick to a plugin, you can mostly skip reading through the study code, through the code of GCC. But another good reason becomes obvious. Like let me ask the audience: how many of you have ever compiled GCC? Was anyone finished under 3 hours? No. Okay. So just imagine you do a little change to GCC and you want to see how well it works just for testing. So you change it and then you compile it and then you wait for half a day before you can test. Yeah, been there. So plugins are clearly the better way to go. Plugins by themselves are shared objects. So you get a shared object that the compiler loads during compile time. A thing that's slightly confusing in the beginning is you compile a plugin that you can feed the compiler, so the compiler can compile other things, which is a lot of compile in one sentence. So essentially you build a piece of software which then helps building other pieces of software. They're maintained by the GCC Path Manager, and they're in a base structure, they're fairly simple to implement. This works as follows on the screen. I'm not sure, you can probably not read this. In the beginning, we see a struct that has to be defined to tell GCC which type of plugin we want to implement. The plugin types, to me, the definition was a bit confusing as well, because GCC says they have CHIM plugins, they provide APIs for RTL plugins, for simple IPA, and for IPA plugins. Whereas simple IPA plugins and IPA plugins from a hackerish perspective are almost the same thing. I'll be talking about that later as well. And then there's another thing that you can do with IPA plugins, which is called IPA LTO plugins, which would be plugins run at link time. If you remember those 4 stages of compilation that I showed you before, like the compiler, the assembler, and the linker happens after compilation. So first you compile the code, then you get an object file, then the linker picks up the object files, and as soon as the linker executes, GCC can load another plugin to work on those object files that are already compiled, which is a bit tricky. So anyhow, I would count like 4.5 types of plugins that we can implement for GCC. This is what we have to tell GCC in the structure that's start up here. Another important thing that we have to tell the plugin is to check whether it's running in the right compiler version. An important thing about plugins is that they will only run with exactly, or like in combination with exactly that compiler that they were compiled with. You cannot run a plugin that they compiled with GCC 6 within a GCC 8 instance, for example. Another thing that's important, we have to specify the path that we want to attach to. So you can either plug in before a given pass or after a given pass, and you have to tell the plugin which pass you want to relate to. What's important there to know is that each pass that GCC executes changes the state of the binary you're compiling. So the whole transition from source code to bytecode, each pass changes the state of that representation. And some of the items that you want to modify, or some of the items that you want to learn about the binary during compilation, might not be available in each given pass. So you have to figure out which pass provides the data structures that you want to use in your plugin. So for example, it's not possible to allocate virtual registers in RTL if register assignment has already taken place. There's one particular pass that performs the translation from virtual registers to hard registers on a given CPU, and after that happened, you cannot allocate virtual registers anymore. I had to learn that too because I tried and of course I failed. Be aware when you try to modify GCC, there's going to be a lot of failing and a lot of learning. It's awesome. And finally, the last point down here says we need a callback. The callback that's specified by the plugin is what defines the actual action that the plugin performs during the compilation stages. All right, and before I go into the dirty details, there's been quite some research that's been done on plugins before, quite some of it also on security topics. I might have wanted to note at the beginning of this talk that right now at Intel, I'm tasked with working and looking into compiler mitigations. So most of my research has been performed on implementing mitigations into the GCC compiler to prototype and test how well they perform. And of course, since I work for Intel, I cannot actually talk about what I really work on. Hence, this talk is mostly motivated by offensive interests. I'll show you later. Anyhow, there's been really interesting research on how to perform the state of security through compiler plugins and compiler internals. If you want to implement them yourself, the best reference that I could find so far was a set of plugins published by a researcher named Emizi Refri. Emizi Refri is, in my opinion, an outstanding software developer that also understands GCC plugins, which is rare. And the plugins are very nicely documented and show a lot of interesting example code. Someone else who published about security research through plugins was a guy named Matt Davis, who published interesting research on how to obfuscate binaries and how to implement stack canaries in different ways. Then more research has been published by the Pincc team, and some of it has actually been presented here at H2HC in Brazil. And also there's an interesting research project called KGuard that is one of the few plugins that I could find that's implemented for RTL. It plugs into the RTL path. And then there's a couple of interesting example plugins by a guy named Roger, who I never actually met in person. Anyway, all right, that was the research. Now let's look closer at the beautiful internals of GCC. I'll get back to my new favorite graphic that shows GCC at a 10,000-foot view, and I can say that the first intermediate representation that you can get in touch with inside of GCC is called generic. If you remember the plugin types, the first type that a plugin can have is chimple, which would be the next intermediate representation. If you look here, that's the next box. But chimple and generic are actually closely related. Generic is, as the name says, a generic representation of input code. That means that any piece of source code that you feed GCC ends up in generic. Generic by itself, I'll show you, it's beautiful. Generic is actually a tree, but it's not really a tree, it's also a language. The documentation said it was inspired by Lisp. I personally, I think I'm a bit too young to have any knowledge of Lisp. I don't know if anyone in the room has seen Lisp before. Yeah? One person? A couple people? All right, I've never done that. You might be happy looking at generic. I wasn't. Generic, one of the log files that GCC spits out is called TU, which for some reason stands for the generic tree representation. And if you look at that log file, you see this beautiful piece of text, which is actually a couple thousand lines long if you feed it a hello world. That piece that's shown on the screen is the printf hello world, so specifically the piece of the main function that calls the printf hello world. This is the whole block of text. You can see in there, like in pink circles, that's the nodes, which are nodes of a tree. So you can imagine you have a function that's the root, then you have a call to an API function in that function that's another node that's below that root, and that function has arguments that are more nodes underneath that root, and it has a return value, which is another node underneath that root. So the whole source code is parsed into tree representation. What more you can see on the slide is the types of the nodes. So each tree node has a type associated and might or might not have values associated. All right, which is terrible for humans to read, but great for machines to analyze. If you have any knowledge of graph analysis, this is basically what the compiler does. It translates the source code to a graph and then does lots of mathematics on it. Very ugly. From a plugin perspective, generic has an API, so you can create nodes on your own. You can assign arguments. You can parse the tree. You can pick out arguments. You can change arguments, which is exactly what the Hail Satan plugin before did. So we searched for the chimple call, which is also a node in the tree, and then we searched for its arguments and replaced one of those arguments. So this is pretty much what it can do in the generic representation. More important though, as a plugin author, you're more interested in chimple. Chimple is based on generic, and they're also, as mentioned, closely related. So each chimple node will have a generic representation. Not each generic representation has a chimple representation. Chimple was introduced so that GCC can add more GCC-specific optimizations. There is a long paper on why they made that decision. I did not read the paper. If you're interested why we have chimple, then you're welcome to read that paper. Anyhow, chimple, from a plugin author's perspective, is much more welcoming than generic. Chimple looks actually closer to source code than the generic representation does. Chimple also stands for the 3 address code. The 3 address code specifies that each line of code in chimple is ideally made up of 3 items. There's a maximum of 2 items, but there cannot be more items in the line. That means the compiler looks at all the terrible code constructs the source code author produced, which might be like an entire line of an if statement. If you code like me, then you might have an if statement and then 25 checks that come after. Anyway, the compiler looks at that and says it's stupid and builds like its own representation that makes it much more simple. In the case on this slide, you can see a mathematical calculation that makes sense to some people for sure. And you can see that the compiler for the chimple representation split it up into the different tuples, which is essentially what you do as well when you remember math in school. You don't solve the whole equation at once, but you solve it like piece by piece, and essentially that's like two pieces at a time that you solve. And the compiler does the same thing. So this whole statement ends up looking like this, which now you can imagine. If you dump the chimple representation of a large application, the output file is a lot bigger than the large piece of source code you fed in before, because the compiler essentially takes all the code constructs out and represents them in a much simpler way, because optimization works much better if the representation is standardized and simpler. That means for us, if we take a piece of source code that's as simple as you can see here on the left side, we have two functions and they perform a simple calculation. Then chimple goes on and translates them to what I've just shown before, to like a much larger piece of code. But you can also see that the whole chimple representation overall looks very much like C code. And the surprising thing is that essentially any piece of source code that you feed to GCC that ends up in generic representation eventually looks very similar to C code. Okay, so you've seen chimple, but now, what does it mean for plugin authors? Chimple by itself, as mentioned, looks much like C, so modifying chimple is not as difficult. What is difficult, though, is figuring out the GCC API to be able to do so. Although chimple comes with statements that look much like from any other high-level programming language, it also provides iterators and APIs to modify statements. So really, if you want to build a quick and simple proof of concept, chimple is the way to go. What's curious, though, as mentioned, is closely tied to tree. So eventually, when you work on chimple, you will always find the tree again. And also, that tree follows you throughout the whole compilation process. So when you go down the different path structures of GCC, you will always again see that tree pop up again. Which is funny, because sometimes you execute chimple APIs and you hand over chimple arguments, and you would expect the chimple return value, but what you get is a tree, because the tree is always there. It's a bit creepy. All right, how does it look inside of the plugin? A quick look back again at the Hail Satan example. Now you can see like we have the iterators on top. Essentially in chimple, you're working on a function by function basis. Our GCC says it's a code, how we say, a code item, like an execution item by item basis. For C, that means you compile a function, then you compile the next function, then you compile the next function, until you hit inter-procedural optimization. I'll talk about this in a bit later. But for chimple, it means that we can always only work on one function at a time. In that function, we can list all the basic blocks that are contained in that function, and then for all the basic blocks, we can walk through the chimple statements. As a reverse engineer, I looked at that and was like, holy shit, inside the compiler, I can see functions, I can see basic blocks, and the compiler doesn't make any mistakes. There's no parsing mistakes, because the compiler produces that stuff. As a reverse engineer that has worked on malware, you're very excited when you see like clear function definitions and basic blocks and stuff like that. That's a beautiful thing. Anyhow, so you can iterate through that stuff, and in there you can then search for a call statement. So any function call inside of chimple will have the type chimple call, and every chimple call has a given set of arguments that you can parse for. If you want to parse for anything in GCC doesn't restrict you much. The C compiler afterwards will restrict you and say like you cannot assign this variable to this value to that variable because types concur or something like that. But inside of GCC, remember that everything is a tree. So in theory, you could take any given type that GCC hands you, lower it down to a tree, and forget completely which type it had. But different types sometimes have different arguments assigned and can only take in different values and only adhere to a given set of APIs. And this is something that the developer has to know. The documentation might tell you some of that, I agree, but again, the documentation has 700 pages. So when you develop GCC, be aware that if you don't check your statement, whether it really has a given type, then you can still run given APIs that will parse the statement. GCC does not complain that the type is wrong, and then eventually the compiler will crash, but the compiler will not know why it crashes because there was nothing being done wrong. You see the problem? Yeah. So we have to check whether we have a call statement at hand, and then we can search for the first argument I mentioned it before and build our tree that represents the string, the Hail-Satan string. So this is a tree by itself, and assign that tree to be the argument of the chimple call. So you see how those two representations are closely tied together. After all of that is happening, first of all, GCC does lots of optimization in the middle. You're able to plug into one of those optimization passes and perform your own optimizations. That's a different set of headache, though, I might want to note. After that, GCC goes on and lowers the chimple representation to RTL. And RTL by itself is a curious kind of beast. RTL stands for Register Transfer Language. Some people might note that some hardware programming language named RTL also exists somewhere out there. That RTL stands for the same thing, but it's essentially not the same kind of language. RTL is specific to GCC, and it essentially implements the machine definition. So after we're done with all the chimple and SSA passes with optimization, the compiler is only interested in translating the code to the final output representation. That isn't entirely true, though. There is still optimization happening in those passes. So the optimization happening during the chimple stages is used for target-independent optimization. During the RTL stages, the optimization that is run there is used for target-dependent optimization, because different CPU architectures might offer different options for optimizing code as it goes. But at this point in time, I want to note that any definite statement that tell you about GCC, take with a grain of salt. Because there's no such thing as totally target-independent or totally target-dependent, since some of the chimple stages already take into account which architecture the code is being compiled to. Because this is something that the compiler knows at all times, right? So they could just propagate that information. And this is exactly what they do. So target-independent optimization is mostly target-independent, and target-dependent optimization is mostly target-dependent. But turns out that the different optimizers in RTL can be reused for other target architectures if those target architectures support the same CPU features. All right, RTL by itself is similar to, no, it's actually not similar. It's an abstract way of describing assembly language or assembly bytecode. With an abstract way, I mean that the RTL statements look like they want to produce x86 or like a given bytecode in the end, but they do not actually adhere to the same rules. RTL by itself is an abstract algebraic language which supports an infinite number of registers and consumes an infinite amount of memory because it doesn't consider any hardware limitations. During the lowering passes of GCC, the hardware limitations are taken into account. And if you remember before, I told you that there's a pass that assigns hard registers. So initially, RTL has a set of virtual registers mixed with hard registers that any CPU architecture that GCC supports also supports. But during the register assignment pass, those virtual registers are translated to hard registers. And afterwards, if we compile for x86, we will see the typical, the stack pointer and the base pointer and RAX and RBX and the typical registers that x86 supports. And there's a funny episode at some point. I was sitting in the lab and I was wondering, like, how can I tell GCC to use a register that will not be used for any other thing that the compiler wants to do with it later on? And the colleague came up to me and like, look at the ABI. And I was like, oh, processor ABI? And another one said, yeah, this is what you look at. Like, why are you even asking? And I was like, okay, I'll look at the ABI. And I looked for the ABI, and guess where I found it? Inside of the compiler. I was really upset. So like, essentially, GCC doesn't just listen to the ABI, but GCC implements the processor ABI. So the machine definitions represent exactly what the processor can do, and the whole process of parsing RTL to a given bytecode output is all oriented by the ABI. So the compiler knows what the output architecture expects. That is a lot of GCC code. Like this is about 600 lines of code only for, not for x86, but for one given architecture. I think I looked at MIPS or something. It's like 600,000 lines of code just for putting a given RTL representation into a given bytecode representation. Anyway, so yeah, that's essentially what RTL does. And I'm finished with that slide. Beautiful. RTL by itself, as mentioned, looks nothing like bytecode or opcode. RTL by itself is a description language to perform abstract descriptions of processor bytecode. In that sense, if you look at this slide, you see two different RTL statements. In RTL, the statements are called INSNs, whoever came up with that name. So we look at two INSNs now. One general INSN that performs a set statement and a specific INSN that performs a call statement. If you would translate that to x86 assembly, you would see that the hello world argument is assigned to RDI, and then the function call to printf is performed. If you look at how function calls in Linux are done, the first argument to a given function call is handed over through the RDI register. In this case, you can see there is the set statement right here in the third line that sets the RDI register, here shortened with DI, because at this point in the compilation process where I took the log file, we already know the registers we want to work with, but we don't yet know which bitness we're looking at. So from this stage, we could still compile for 32-bit or for 64-bit, which is why the registers are shortened here. Then you see that the RDI register is loaded with a symbol reference, which goes to .lc0, which is somewhere in our data section at this address that it will have in the future, which we could now guess that holds the hello world string. Something that's occasionally annoying about RTL is that it doesn't know anymore which pieces of data the application consumes. So when we enter the RTL stage, the constant of hello world has already moved to the data section of the output file, which means that we don't actually have access anymore to that hello world string. We just see the symbol reference that references an offset in the data section of the compiled binary. That is annoying if you want to come up with a proof of concept that replaces hello world with Hail Satan. There is no more hello world when you look at the RTL representation, which is the reason why I wrote the Chimple plugin. Anyhow, so here we see that RDI is loaded with the hello world string, or like with the offset to the hello world string. And down here we see a call INSN, which again starts with a set, which is curious. Set in this case sets the return value of the function that is going to be called. So with this first statement, we say that REX is going to hold the return value of this function. That means for the compiler that REX should not be, like if REX is being used before this instruction is executed, that it cannot be trusted after this instruction is executed. This has nothing to do with what the function tries to do. The function will need to place its return value into REX. This is defined by the calling convention that was used for implementing that function. For the compiler, that just means that this register will be clobbered. That means that, again, if it's used before that instruction, it cannot be used again after that instruction, because it is dirty. Then you see the call statement, which calls puts. If you've looked at Linux binaries, they translate every printf to the library-specific function. In our case, that's a put string. And there we see that no, sorry, that's it. We don't see anything more interesting in here. You see that the puts instruction, the puts function is being called, and that this is the argument that's handed over through RDI. So this will be if you wanted to translate this piece of text to x86. But keep in mind, this piece of text could still be translated to ARM or to MIPS or to anywhere else. Or maybe not, because the register assignment worked. Anyhow, you're still independent from x86 at this point in time. The representation itself, I've been talking a lot about it. I've not nearly described how it really looks like and how to work with it. RTL by itself is made up of objects and object types. The instance that we've been talking about are mostly RTL expressions, which means if you want to set the register with a certain value, that's considered an RTL expression. You tell the compiler, you teach the compiler RTL expressions, and the compiler produces instance statements. Whatever you do with compilers, usually you look at it from two sides. So if you want to produce x86, you have to tell the compiler to produce x86. If you want the compiler to produce instance, you have to instruct the compiler to produce RTL expressions. This is how GCC works, don't ask me why. We have different classes in there. So instead of RTX instance, which would be like general sets, we can also generate compares or calls or returns. Those are different types that are supported as a generic representation. And of course, we have to consider machine modes. Before I told you that at that stage where I took the log file, we could still decide whether we wanted to go for 32-bit or for 64-bit. This is essentially indicated by machine modes that you have to hand over to an RTL expression to tell the compiler which machine mode you're compiling for. This is important as a plugin author because occasionally you get funny errors when a variable doesn't fit a certain space or something. That usually means the error that GCC gives you says invalid instance length. And that means most likely that you've confused the machine mode somewhere and assigned the wrong width of your piece of memory or your register that you're working with. Then finally, from a plugin perspective, we're as close as we can get to the x86 layer. That also means we have more power than we might have ever wanted. When you modify RTL, be aware that many parsing stages where the compiler watches out that the author can't do anything wrong have already happened. So that stage, the compiler looks out very little for your mistakes. That means if you modify a register in an RTL pass and you forget that that register is used later on by the function for different things or is used by the compiler for different other activities, then you have to tell the compiler. You cannot assume that the compiler will automatically know and use different registers for the tasks that are lying ahead. An interesting problem that I had there was position-independent code. Position-independent code leverages the RBX register to load a given table that it needs for execution. And turns out if you use the RBX register for something else, then the position-independent code afterwards will not run. As curious as it is. A benefit, though, from working on RTL is that we're also as far away from optimizers as we can get. Optimizers are sometimes very annoying when you try to modify something that's specific to a given architecture. So, for example, if you try to introduce a stack canary in Chimple, you can most likely go ahead and do that, but be aware that a compiler, like especially an optimizer, thinks that stack canaries are really stupid. So a compiler looks at that and says, like, this is useless code, let's take it out, which might not have been what you wanted in the first place. So when you do modifications, be aware that the optimization passes that run after your given pass could still destroy your work and make it useless. And finally, if you want to implement anything in RTL, look at the log files rather than the documentation. I mentioned that before. Here's some example on how to actually write RTL. So if you're going at it with a plugin, you have to use the API to issue RTL expressions. And that means that for any given assembly instruction that you want to issue, you have to, in most cases, you have to call at least 3 or 4 functions to actually get to your output instance. So in the first example, you see an LEA instruction. In the second example, you see a push instruction. And in the third example, you see a move instruction. And the move is fairly straightforward because, as mentioned before, we have the set, this construction of set, which just sets one value to another, which is pretty simple. But for example, if you want to push a value, the compiler needs to be aware of where the stack is and what the stack is and how to access the stack, which memory modes we need to accessing the stack, because the stack could be 32 bits wide, or it could be 64 bits wide, or it could be whatever bits wide that the CPU architecture defines. And we need to modify the stack pointer. So if you push something on top of the stack, you need to know where the stack is, and you need to modify the stack pointer to update it to jump one ahead, which is usually what push does. If you remember, the push instruction does different things. And if you're inside the compiler, you have to emulate those same activities, just so that the output is still intact, which is very tedious. All right, now I talked about 30 minutes about compiler internals. Here's the last stage, the machine definitions. The machine definitions are fairly boring if you look at it. The machine definitions describe how the output instructions for a given architecture look like. And they're made up of different files, where the most important one is the architecture.md file. And that looks, as shown on the slide, like very ugly again. By the way, when you work on GCC, you look at lots of text files that all show you different representations of the very same thing. So in this case, we see a machine definition, a define inzen for a sub, which defines how the RTL looks like that is needed for describing that sub. If you want to generate a sub, you will have to issue all of those RTL constructions. And then how the output sub looks like as text. I mentioned that in the beginning, the first stage of the compiler produces text files. I was stunned when I saw that first. In theory, you can issue, you don't want to do this is bad practice, but in theory you can issue a printf inside of a print file inside of a GCC plugin and print directly to the assembly output file. You will most likely mess things up there and break things and make everything unrunnable, but you could do that. You could print st text to the assembly output and not do all of what the compiler asks you to do. All right, finally, if we step through all the different passes in GCC, there's still the interprocedural passes, which help us look at the whole piece of code that we want to compile. I'll make this quick. So in Chimple, for example, you look at the function, I mentioned that, and inside of an IPA plugin, you look at all of the functions together. So there you can parse from function to function and perform changes that have to know how the whole function call tree looks like. And I'll skip most of the rest of the slide because I think I'm running out of time. Finally, additional wisdom. GCC plugin troubleshooting, it's very important. This is what you do most of the time when you write plugins. You try to troubleshoot. GCC isn't very helpful with putting out error messages when your plugin fails, because GCC thinks that the source code that you fed the compiler is a problem, not the plugin. GCC is aware that there's plugins running. It will tell you when you execute a plugin that it is running a plugin, that you should check the plugin, but it does not tell you where in the plugin the compilation is failing. That means that you might be looking for a mistake in your source file, while the mistake is actually inside the plugin. Very helpful there is to verify the stage that you're plugging into, like know what the passes before and after you are doing, before you do your own modifications, so you know which data structures are available and which might not. And, of course, look a lot at GCC source code. The first most helpful thing I found was the log files. The second most helpful thing I found was wobok.com, which lists a very nice static analysis of the whole GCC source base with cross-references and inline documentation, everything that Linux users don't usually have. I'll admit I spend most of my development time on Visual Studio, where static online code analysis isn't really a thing because Visual Studio does all that. And on Linux, you're a bit lost on that. If anyone has a better idea, I'm open for suggestions, but I'm still a very big favor of Visual Studio in that case. Anyhow, yeah, the debug logs, and of course you can also go debugging GCC. If you go debugging GCC, be aware you have to compile a debug build of GCC, and you want to debug the first stage of the compiler. This is where I found out there's different stages of the compiler that they can debug, because if you try to figure out why your plugin is not working while you're debugging the assembler, you're wrong. You have to debug the other binary, just as I've mentioned. And also finally, you can write RTL in a simple C file. So there is an option in GCC that you can define inline RTL, which is somewhat ugly, but you can do that. And you can write RTL in a simple C file and test your code before you shoot sharp with plugins. All right, that was all the theory. Finally, let's have some fun. As mentioned, at Intel I mainly work on mitigations, where I cannot actually tell you what I'm doing there. So for this talk, I worked on the opposite. I tried to unpatch code instead of fixing it. So finally, for the demo, I looked at the bug. I don't know if she's in here right now. So 2 months ago, I attended a code security workshop by Natalie Silvanovic, who gave a talk yesterday on exactly that, on code security. And she showed us a very simple bug in SQLite that looked funny when when you look at the source, there's exactly one check missing that checks whether a given size argument that's being decreased in a loop eventually hits 0. So that check isn't there. So when certain conditions are true, that size argument will go into the negatives. The size argument is afterwards used for a memcopy call. So the memcopy will eventually copy stuff God knows where. All right, and this happens when you feed the SQLite library a journal file that is usually generated by SQLite itself, but you can trick SQLite into loading a custom journal file, and if you take out the dash, the size variable will decrease until unknown. All right, so what did I do? I looked at this bug and I said, like, that's interesting. So SQLite actually patched it. There's now a check in the loop. If you download the latest version of SQLite, this cannot happen anymore. So I downloaded the latest version of SQLite and saw whether I could actually remove that check. For doing so, let's have a quick look at the source. So this is the problematic piece of code where you can see now there's like an if statement and it says if ndb equals 0 or other condition, return. This wasn't there before. Thankfully, they noted that in the command, and it turns out that many open source projects actually leave those comments, like they put in a patch and they comment why they patched, which is when you go and want to remove patches, this is awesome. There's like flags in the code that tell you where. Anyhow, so if this check wouldn't be there, then the loop would be searching for like a dot or a dash. And if it wouldn't be able to find those, it would decrease NDB until unknown, until eventually somewhere in memory it would hit a dash. This is then the value that is handed over to memcopy, which at that point in time might have any value, any unknown value. Memcopy would then try to memcopy something somewhere. This is the folder that I'm working in. There's a couple of files in there, and in the end you see a test DB and a test DB journal DB. I might want to admit for triggering the bug, I built myself. I cheated. I built myself an easier path to get to the actual bug. But what I'm triggering right now is still the same bug. It just makes the proof of concept a little easier. Anyhow, let's look at the whole thing with the patch. So if I go ahead, I have a makefile here for SQLite. If I go ahead and compile SQLite with this command line that you can see there, that says nothing but minus LDL, minus LP thread for loading libraries, minus shared, minus pick for being a shared library, minus O0 because I don't like optimization, etc., and spits out libsqlite3.so. Now I have my DB test application, which goes ahead and loads the database file without a dash and without a dot, loads this, and with the patch, SQLite says that it could open the database successfully. So we're happy. Everything's secure. But now, when we go on and execute the same thing, now with the -f plugin equals to chimple@tecker.so. That's my very creative name for my plugin. We will see that this patch isn't there anymore. My plugin does a little bit of output, where you can see I looked for that specific vulnerable function. Then I looked for the memcopy call in that function. Then I looked for what the argument for the size was like. In this case, this is _8. _8 isn't really the variable we're looking for. If you remember, the chimple representation was split up every mathematical calculations. In this case, since we have the decrease, like the subtraction happening on the size argument, this is a virtual variable for chimple. So here we have _8. Then in the compiler, we have to follow up _8 and find the actual assignment until eventually we hit the NDB variable. Then we have that variable, and when we know which variable represents our size argument, we look for conditional arguments that check that particular variable. And there eventually we find the if NDB equals 0. So when I found that, I can just remove it, right? And then when I run my very same database application with the unpatched library, all of a sudden we run into a segmentation fault. So there we are, we've successfully unpatched SQLite. This isn't about nearly as exciting as if I would have popped the calc on stage, I know. I'll apologize for that later. Happy memory corruption. How did that look like if we look at the assembly? This slide has to be looked at from the left side first. So here you see the patched version. You can see in there, those two lines are the actual patch. There we look at the size argument, which in this case is located in the stack, and check whether it's 0. And if so, we jump to the return. We will return an SQLite OK. So if that is in there, then any database or any journal file without a dash and without a dot and anything will work just fine. After we compile it with the plugin, though, this patch is missing. So if you look here, this is like the same jump instruction. This move instruction down here is the same one as you can barely see down here. So here it's just those two lines are gone. That means we unpatched the target binary and ran into our memory corruption. How did I do this? Just to sum it up real quickly, I searched for a chimple call, checked whether that chimple call was a mem copy, searched for the size argument of that mem copy, walked up the function, searched for sanity checks on that size function, and removed them. You might know that this is possible, like in any given application. So you don't have to stick to that one particular bug. I tried it too with SQLite. There's actually various different occasions where mem copies are fed with size arguments that are checked before whether they're 0, because they're decremented on the way. So this happens quite often. In theory, you can remove all of those sanity checks and just try to exploit like any bug. You can create as many bugs as you want. But the problem there is that you have to watch out to not ruin the actual application. So like if anything that you're removing is used by the application flow and is actually required to be able to execute properly in a normal setup, then you might be screwed if your victim tries to load the database file and it just doesn't load. Like you can't exploit something that's not running, right? So you might want to make sure that your plugin doesn't remove healthy things. All right, finally, who would do such things? Supply chain attackers, like attacking compilers, is something that's been noted in the literature in a long time. Actually, been mentioned the first time in 1984 by a guy, I forgot the name now, but he gave a speech after receiving his ACM Turing Award and showed an example of putting a backdoor into a given application using a compiler. So that was the thing in 1984. You can still do that today. There's no real good solution for the problem. People can go and, of course, watch out for the security of their build system, which is very healthy. They can verify third-party code, which is very difficult. If you build open source software and you use other open source software to build your open source product, then you usually don't have the funding to look at millions of lines of code in an assembly representation to check whether anything happened during the compilation process. A similar problem, by the way, is optimization bugs. That's another field of research that people have worked on in the past, and that's so far fairly unsolved. And as an attacker, pretty beautiful. If you can get your hands on the build infrastructure of a large company, then oh my God. All right, yeah, finally you can do continuous build verification. Like you produce your software, you don't look at the actual assembly representation, but you keep testing and fuzzing, and you have a great security team that does all that for you, which is what I do at Intel. All right, that was the presentation. If there's any questions, I'm happy to take them now. Otherwise, thank you very much for your attention.